Today I wanted to make a video about anomaly detection and how to use anomaly detection in Python, in particular using Scikit Learn. Scikit Learn has a few neat models that we can use for anomaly detection. In the field of anomaly detection, we can define two categories of anomaly detection algorithms and methods. We have outlier detection and novelty detection. The main difference between the two is that when we are using outlier detection, we start with a dataset and we want to detect the outliers and the anomalies within that dataset. That is, those observations, those data points that are the most different from the other data points within our entire dataset. When it comes to novelty detection, we start with the initial dataset, and whenever we receive any new data points, we compare it with our initial set of points, and if they are too different from our initial dataset, in that case they're considered novelties. So these are the two types of anomaly detection problems that we're trying to solve: outlier detection and novelty detection. Usually outlier detection is considered an unsupervised learning problem. That is, we can start without any type of supervision. And novelty detection is considered sometimes as semi-supervised because we already technically start with a data set, and we consider our initial data points as being non-anomalies. Within Scikit-Learn, as you might be already familiar, for many types of models, you usually have the two methods, fit and predict. That is, you use fit in order to essentially fit a model on your initial training set, and predict is always used to essentially label any new data points. So usually what happens is that you'll create an estimator object based on the classes that you have from Scikit-Learn for each individual algorithm. You would fit your model, and then you'll use the estimator to get the final labels. All the different anomaly detection algorithms within Scikit-Learn have a similar API in terms of always outputting a 1 if a particular data point is considered not being an anomaly, or what we call an inlier, and -1 if the particular data point is considered an anomaly or an outlier. For some of these algorithms, you also have a method called decision function that will also give you a score that will give you that will tell you essentially how strong is the conviction of the algorithm that a particular data point is an anomaly or not. But there are exceptions to this, in particular the local outlier factor algorithm. In that case, you don't have essentially the predict and the decision function methods. You just have the fit predict when you're using this particular model for outlier detection, that is for unsupervised anomaly detection. You can have these methods when you're using the local outlier factor for novelty detection. However, in that case, again, sometimes it might not always be useful to use this decision function and the score. So again, you have to be aware of this whenever you're using your anomaly detection algorithms, and always be aware of the type of problem you're applying your algorithms to. So now that we defined what anomaly detection is, and also we've reviewed the two main types of anomaly detection within Python, that is novelty detection and outlier detection. Let's have a review of the main algorithms that we can use in order to detect outliers and novelties. So among them, we have what's called robust covariance, and is implemented by the elliptic envelope algorithm. We also have the one class SVM, the isolation forest, and also the local outlier factor. As you can see in the Scikit-Learn documentation, we have a few example datasets on which each one of these algorithms was applied, and you can see with orange the data points that are detected as not being anomalies, and with blue all the data points that are detected as being anomalies. So if you look closely with the robust covariance / elliptic envelope, we essentially fit a Gaussian-like distribution over our initial set of data points, and essentially we end up with these kinds of clusters of non-anomalies. and any data point that is found outside of these clusters is considered as an anomaly. We tend to get quite a similar result with one class SVM. Then, in the case of the isolation forest, as the name implies, the isolation forest is built in an unsupervised manner by several decision trees. So you might be able to notice that the decision boundaries tend to be quite straight. That's because essentially we have all of these if-else conditions within the decision trees, and you essentially wouldn't end up with a round decision boundary between anomalies and non-anomalies. But in practice, this approach tends to work pretty well quite often. And as you can see, it's also able to figure out whenever you have two separate clusters, and it separates them. And also the points that are situated between these two clusters don't necessarily need to be considered as inliers. They can be considered as anomalies. While, for example, in the case of robust covariance or elliptic envelope, these several data points over here are considered inliers, even though you can see with your naked eye that they kind of don't look as inliers. They could definitely be considered outliers or anomalies. And another approach is the local outlier factor. If, say, isolations forest could be compared with other decision tree based models like random forest or extreme gradient boosting, extreme gradient boosted trees, local outlier factor could be compared with, say, k nearest neighbors, because it's essentially a density based approach to detecting anomalies. And as you can see, it can have it can detect different clusters of non-anomaly data points. And one particular feature of local outlier factor is that whenever it detects a cluster, it doesn't need to be to have the same density as the other data points in the entire data set. So for example, this would be a good example. You have this particular cluster where the density is much lower compared to, say, the density of the data points in this particular cluster. So they're considered as two separate clusters, and these are still considered as being non-anomalies, even though the distance between the points in this second cluster is much higher. So again, it's a different approach of looking at our data set. For some applications, might be a better approach. And also again, for some other applications, you might consider merging these several approaches into one ensemble solution for your anomaly detection use case. Let's talk about novelty detection. As we mentioned, this is one of the two main subsets of problems within anomaly detection. And essentially the problem that we're trying to solve here is, say you have a data set, and over time you receive new observations. It can be, say, you start with a set of observation from, say, a sensor, an IoT sensor or multiple IoT sensors for various industrial applications. And you constantly receive data. You constantly receive data points, and you want to figure out whenever a particular anomaly appears. You don't have a very good idea from the very beginning about what an anomaly would be. However, you do think that all the data points and all the measurements that you have so far are considered normal. So in that case, what you can do is essentially compare all the incoming data points, all the incoming data with your existing data, and try to figure out if the new data points are in any way similar to your original data. And the way you could do this is, for example, using the one class SVM algorithm, which essentially would try to learn some kind of frontier around your initial set of data points, your initial set of observations. As you can see, for example, in this particular plot, with white, you have all the initial observations within our data set. And then we receive new observations. Some of them are labeled with purple, those that are very similar to our original data, but also with yellow, some data points that are quite far away from what we are used to from our initial set of data points. So essentially, the one-class SVM algorithm tries to find these boundaries, these red circles were curves around our initial data sets. Any new data points that fall within our learn frontier, they're considered as regular observations, while any data points that fall outside of this frontier are considered novelties. And essentially, that's how this algorithm works for novelty detection. We can also use the local outlier factor for the same problem. For novelty detection with local outlier factor, we essentially start by instantiating the local outlier factor estimator. It's very important to set the novelty parameter to true. That's because local outlier factor can be used for both novelty detection and outlier detection. And in this case, we want to set it so that it detects novelties. Then we fit the estimator on our training observations. And we would be able to predict for incoming new observations, whether they're inliers, that is regular observations, or outliers or anomalies, that is abnormal observations, as you can see here represented with the yellow. So this would be novelty detection with local outlier factor. Now that we covered novelty detection, let's look at outlier detection. The simplest way to think about anomaly detection for a particular data set is to think about the fact that the data from that particular data set comes from a particular distribution. And what is the most common and the simplest distribution known in statistics and in data science? Well, it's the Gaussian distribution or the normal distribution. The first method we're going to look into, that is elliptic envelope or robust covariance, literally tries to fit Gaussian distribution over our initial set of data points, and whatever data points fit the best within that Gaussian distribution are considered inliers, that is normal data points, and all the other examples are considered outliers or anomalies if they do not fit very well into that particular Gaussian distribution. So you can see here a good example with this data set. You can see that we have a cluster of black data points that are clustered together around this area. And we also have a few sparse data points around this cloud. And our elliptic envelope algorithm is capable of figuring out the fact that most of our data is clustered along this particular area, and is able to fit the Gaussian distribution on top of it, and is also capable of figuring out that all these other points that fall further away from our fitted Gaussian distribution are actually outliers. If you've used tree-based models before for supervised use cases, you probably already know the fact that they can be very accurate, and they can also provide solutions quite quickly, say compared to neural networks. It might sound a bit surprising to know that there are use cases for tree-based models in the area of unsupervised learning as well. And that is where isolation forests come into play. They're called forests because they're composed out of multiple decision trees. And the reason they're called isolation forests is because within the process of constructing each individual decision trees, The goal is to isolate individual observations from the rest of the dataset. Why is that important? Well, essentially, when you start with a feature at random and you try to split the data points based on the values of that particular feature, and you try to do this repeatedly, recursively, and randomly, you will end up essentially splitting all the data points in your dataset into individual clusters. And if you do this repeatedly, you will end up with individual data points in each one of the leaves of the tree. And if you think about it, all the data points that are situated closer to the root of the tree require less partitions, and they are more likely to be different, much more different from the rest of the data points in your dataset. While the ones that require more splits are usually clustered together with other data points. Hence, you always have to um, um, do additional splits. So if you end up with, say, a cluster of data points in one particular branch, you then have to split that on a particular feature, and then you have to, and then you obtain two different clusters that again have similar data points to each other, and then you have to do a split again and again and again and again, and it takes quite a while until you split all those data points that are clustered together. So if we want to isolate, say, one particular anomaly data point, we might be able to do this successfully for a particular decision tree, but then for the second decision tree, it might take quite a larger number of splits until we are able to indeed isolate the anomaly. But then if we do this for, say, 10 decision trees or 20 decision trees or 50 decision trees, it's much less likely that we will be in a situation where anomalies are detected later rather than sooner. So that is the main reason why we want to do this process repeatedly, and we want to build a forest as opposed to just relying on one individual decision tree. And we have here an example of how isolation forest would be used. So again, we are building all of these decision trees within our forest. Because of these if-else statements, you see these straight lines that split our plot. And essentially, the brighter the color, the more likely is that data point that would fall within these areas would be considered a normal data point. And if it falls within one of the darker shades, in that case, the probability is higher that those particular data points will be detected as outliers or anomalies. And you have here code example in Python on how you can use an isolation forest. You have this dummy dataset that you can fit with your isolation forest estimator. You can set here the parameter and number of estimator, that is the number of trees. And yeah, essentially this is how you'd apply the fit method in order to be able to train your model. We talked earlier about the local outlier factor in the case of novelty detection. We can also use the local outlier factor algorithm for outlier detection when we want to detect particular anomalies within an existing dataset. So as mentioned before, the local outlier factor can be thought of as being similar to k-nearest neighbor. In terms of the algorithm itself, it's usually recommended to be used in cases where you have multiple densities of data points within your data set. And you might want to detect as clusters of normal data points, clusters with different densities. So, say in a particular cluster, you might have a higher density. In another cluster, you might have a lower density. Um, but you wouldn't want the data points in the cluster with lower density to be detected as outliers. In those cases, it's much harder to use, say, elliptic envelopes or isolation forests, because they will not make distinctions between the different densities within each cluster. To show you what I mean, I always come back to this particular example. I think it illustrates very well the point that in this particular cluster we have a much lower density between these data points, and for some algorithms it might be the case that either all the data points in this cluster or some of them will be detected as being outliers, for the simple fact that well, they are situated at higher distances from many other data points. And you can actually see, for example, in the case of isolation forest over here, this group of data points are considered as outliers or anomalies, while in the case of local outlier factor, they're still considered as part of the cluster of normal data points. So this is actually quite important. And also in the case of detecting anomalies, it might be the case that certain data points in a high density area of your data set might be indeed anomalies. So you can see here these data points on the boundary of this higher density cluster are considered anomalies, while for most algorithms that wouldn't be the case. So again, it's really important to think about um, what actually defines a particular outlier or a particular anomaly in your scenario or in your use case. Usually what is best is to try all of these particular methods to understand your data set, to understand the strengths and weaknesses of all of these approaches, and figure out whether you want to go with one approach or the other, or again, whether you might actually want to combine multiple approaches together. The local outlier factor algorithm uses the concept of local densities in order to decide whether a particular data point is an outlier or is an inlier. The concept itself of local densities is quite complex, and unfortunately I wouldn't have time to cover it in this particular video. If you'd want me to cover the concept of local densities, please leave a comment down below. So that is our short videos about anomaly detection, outlier detection, and novelty detection using Scikit Learn and Python. If you found this content useful, I encourage you to like this video. If you want to stay in touch and receive notification whenever I release new videos related to data science, machine learning, AI, please click that subscribe button and also hit the notification bell if you want to get notifications as soon as possible. Thank you very much for watching this video, and see you soon.